Okay, it's 1 o'clock, so we'll go ahead and get started. So first off, let me welcome everybody to our almost bi-weekly chats about Green Bank Observatory and what's been going on with the observatory. So today we're going to start off with a bit of observatory news. Myself, Toney Minter, and Jay Lockman will give you brief updates on some of the going-ons at Green Bank Observatory and with the GBT. That's mostly information, and we'll try to keep it fairly short because after that we get a fantastic talk by Karen Masters to just give us a brief overview of the HI-MaNGA project. So that'll be definitely the highlight of all of this. So with that, let me go ahead and get started. So Green Bank Observatory is in the time of COVID, the state of West Virginia itself, the cases have remained around 2 to 4% of all cases. All tests have been positive for COVID-19. And this has been a fairly stable number for about a month and a half now for the state. Little bumps and wiggles, but nothing else. We, of course, have a requirement for masks indoors within the state of West Virginia, as is true for most states in the country, as well as restrictions on the number of people that can be gathered together at any one time. Locally, we look at the fact that across the state we're having school sports, that's soccer, football, cheerleading, and other sports are starting next week, with schools starting the week of September the 8th. And so we anticipate some changes in the numbers of COVID cases as that moves forward. Nonetheless, the GBT, as I've been saying all along, remains in full operation throughout all of this, and we're managing to have our work continue, and I'll talk more about that in just a couple minutes. However, all our visitor programs remain canceled. The fact that the number of cases is really not decreasing at the level we'd like to see is worrisome, plus knowing that with the schools opening, we have the potential for seeing an increase in cases. We'd rather wait to open up until we know we can safely open and stay open than open and have to close again. But with that, I thought I would take just a couple minutes of your time to show you a little bit about what it means when we say that we remain open and operational 24 hours a day, 7 days a week. So this is what it looks like to the staff that come on work. Of course, about half of our staff are working from home and may not even get to see the site at all. You might not have seen it since early March, but for those people that are coming in, it looks about like this. We've set up a health check for all the staff that come on site. And they come into the building, and here you see one of our employees who works at this health check doing a temperature check of all of our staff as they come into this building, and then also asking questions of our staff, just going through the COVID symptoms to make sure that nobody's experienced them and nobody in their families experienced them. This is something that happens every single morning, so if you come in 5 days a week or even 7 days a week, you're going to go through this health check every single time that you come through. This is mostly a reminder to make sure people have been thinking about their health and taking precautions. Of course, if anybody were to not pass this health check, they would be asked to go home, and then we would work with them on their next steps. So what does it look like in practice? This is just a few pictures that I selected to show kind of people doing the various jobs here at the observatory and what it looks like. So everybody gets to wear a mask, face protection at all times, even if you're working, as you see in the one picture in the forklift, fairly isolated. We want to be as safe as possible. We really want to make sure that all of our staff, anybody on our site, is as safe as they possibly can be. So you can see a few pictures of that. You can even see it up on the GBT itself, where we have 3 people working up on top of the receiver room down in the bottom left corner there. And whenever possible, if you don't have to be near each other, people are separating out, keeping their masks on. Again, just doing everything possible to stay safe and to keep our staff safe. The result of this has been fantastic. We haven't had any cases of COVID-19 on site that we're aware of, and our staff have been able to continue to work. So one of the big bonuses of this continue to work, and a little bonus of stepping in and getting to see these meetings, is sometimes you get to see pictures before anybody else. And so yesterday we had a very exciting moment on site, which is the weather box, the mounting box for our Lassie system got installed on the telescope. So Lassie, again, is a laser scanning system that we're putting in place to scan the surface of the GBT and then provide real-time feedback so that we can optimize the surface even at the highest frequencies, potentially opening up significant amount of time even during the day for high-frequency observing on the GBT. And so we've been working on this project for quite a while now. Yesterday was a big moment getting the weatherproofing box up there and installed. Today they're up putting the fibers in, and then hopefully, depending on the weather, we'll actually put the instrument inside of the weather box either this week or early next week, depending. The system you see here is on rails, and that allows us to retract the system if we need to for safety reasons, as well as to have it out hanging over the dish whenever it's possible. So those are kind of my slides, and I'll go through quickly the couple of questions that have come up, and then hand this off to Toney Minter. So the one question that came up is on the impact of the closure of Arecibo. So those of you that don't know, Arecibo had a extremely unfortunate accident yesterday morning, or early yesterday morning, where one of the cables on one of their towers snapped, causing damage to both the surface, the dish itself, as well as some damage to the Gregorian dome. We're incredibly saddened by this news. We have all of our support and good thoughts thrown the way of the Arecibo staff as they work on plans to recover from this. Nobody was hurt. And I encourage you, if you would like to learn more about this, to go to the University of Central Florida page where they have an announcement about this. To answer the actual question that was asked, does it have an effect on the GBT? Not directly, in the sense that although we are sister observatories and certainly work hand in hand, we do run separate processes and separate tasks and so forth. However, if Arecibo does have to remain down for a period of time, we do anticipate some of the science that would otherwise be normally done at Arecibo being moved over to the GBT. And of course, unfortunately, it means that any of the biostatic radar observations that we would have done with Arecibo will have to be put on hold in the near future. So that's the direct effect it has on us. And as I said, that our hope is that Arecibo could find a path forward and find a way to get the dish back up and running again with all speed. So certainly our thoughts are with that team. So with that, I will hand this over to Tony Beasley to give you guys a little bit of news about the GBT itself. And I remind you guys that if you have questions, please put them in the chat or into the Q&A. Either one is fine. So Tony, it's all yours.
All right. Okay, hopefully everyone can see the screens I put up. Is that the case?
Yes.
All right, so we had a good number of proposals submitted at 21A deadline on August 3rd. Those have begun the review process, and we're not allowed to really say anything about any of the proposal handling numbers, statistics, until disposition letters go out. And those should go out sometime by mid-November. So that process has begun, and we'll remain fairly silent on proposal handling until the disposition letters go out. As Karen mentioned, Lassie is installed on the GBT, and it will begin its performance testing this fall and continue through the winter. And then once the performance is characterized, we'll then take a look at how it can be moved into actual use during observations. So we have a couple upcoming virtual workshops. We have the Wider and Deeper at Green Bank, the new Argus 144 instrument. The poster submission has been extended through September 4th, and registration is open until the week of the meeting. And also should mention that the schedule is now online. If you go to the meeting webpage, and the registration link is given there. Also, observer training workshop coming up in October is almost nearly full. There's only a few remaining seats available for that. So if you really want to attend or have a student or someone who wants to attend, please register very soon. And our next workshop, we're tentatively looking at having one in February, the exact dates to be determined. And that is everything that I have. Turn it over to Jay.
You are muted, Jay.
Okay, now can you hear me? Yes.
Yes.
Just a brief reminder to everyone that we have a new joint agreement with, and the slide I'm showing is from a presentation that the SOFIA Science Director, Margaret Mixter, made just an hour ago. And I just want to point out that the last thing on this slide is the partnerships with ground-based observatories, and Cycle 9 call has joint programs with the GBO, the GBT. And so what this means is that observers submitting for the primary project to SOFIA can at the same time request supplementary data from the GBT and get it without it being scientifically reviewed by the GBT. So you don't have the double jeopardy. This is just the most recent of our engagements with other observatories. We've been running programs like this with HST, Chandra, Fermi, and others for a number of years. And so now we're joining SOFIA. And that's all for me.
All right, so thank you, Jay. So that concludes the part of this, just giving you a little bit of background and some of the fun stuff that's been going on at the observatory. And with that, I'm very happy to introduce Dr. Karen Masters from Haverford College, who is going to be talking to us about H1-MaNGA. So with that, Karen, I'll hand it off to you.
I did the unmuting thing as well. Yes, there we go. I want thank you very much for the invitation to come and give a talk about this work that we've been doing with the Green Bank for some time now. So the title of my talk was H1-MaNGA, H1 Follow-Up for the MaNGA Survey. So I thought I should start. There we go, by explaining what MaNGA is. So MaNGA is an optical spectroscopic survey of relatively nearby galaxies in the redshift range of 0.025 to 0.15. It's part of Sloan 4. So the SDSS is still going and is still observing every night at the Patchy Point Observatory in New Mexico, now entirely spectroscopic, and MaNGA is one of the 5 surveys that make up SDSS 4. What MaNGA does that's new and different from previous Sloan spectroscopic surveys of galaxies is that they were single fiber optical spectra. So for nearby galaxies, and this is my kind of cartoon version of this here with this beautiful barred galaxy and a little black circle in the middle, nearby galaxies, the optical spectra was just a tiny fraction of the galaxy that you're sampling. Whereas MaNGA has these arrays of fibers in hexagonal arrays from 19 to 127 fibers in each of the bundles. And so it's able to get a spectral map of each galaxy. We've been observing with MaNGA as part of Sloan 4 since 2014, and we finish soon. We finish, well, that's a little bit up in the air, but we will be finishing in the next few months. And the goal of MaNGA was to get a sample of around 10,000 galaxies. Okay, so what does this data look like? So here is the first observations for MaNGA. This was the March 2014 commissioning plate. MaNGA, it runs in this fiber optic fed plate system that SDSS is famous for. And because we bundle the fibers, we don't get 1,000 galaxies per observation, but we still get 17 galaxies per observation. So every time we get a new plate observed on the telescope in New Mexico, we get 17 more galaxies. And there's a distribution of different bundle sizes on each plate. So 5 of the big ones, 2 of the little tiny ones, and a distribution in between. So this was the commissioning plate. So we took an observation of this interesting Markarian object, which has Hubble Space Telescope imaging, which you can see here. This is the Sloan imaging of that same galaxy, and you can see then the MaNGA imaging quality. It's 2.5 arc-second imaging that you get from MaNGA, but instead of each pixel just being, you know, a couple of filter bands, you actually get a full spectrum, a full optical spectrum at each pixel. So it goes right across from just short of 4,000 to over 10,000 angstroms. Can you hear the thunder? It's very loud thunder where I am right now. Anyway, that's what that is if you can hear it. Okay, so that's one plate with MaNGA, but the game with MaNGA is lots and lots of galaxies. So MaNGA will observe, or it has observed, around about 1,400 galaxies every year over the last 6 years. So that adds up to about 10,000 in total. And this is a set of just short of 5,000 galaxies. So we're showing the color magnitude diagram. So this is optical color, optical magnitude. You get the red sequence and the blue cloud. And then this is stellar mass star formation. And the background image here, made by Carl Westphal, is, in this case, it's little G-band kind of optical images of each of these 5,000 galaxies through the bundle. We get lots and lots of data. So if I flick through this, you also get the H-alpha image for every galaxy or any emission line that's in the spectral range. This is obviously tracing star formation or other ionization. D4000 is really popular with optical astronomers. This is a break of 4,000 angstroms in the spectrum that correlates with the age of the stellar population. So the bigger this is, the older the stars are. And obviously velocities as well, since this is spectral data. So here's the stellar velocity, but we also get gas velocity from any emission line that's detected. Okay, so MaNGA is a lot of data. And this is a part of SDSS. So we have regular data releases via the SDSS procedures. And this is a lot of words on this slide, but this to sort of summarize the current public version of MaNGA data is just short of 5,000 galaxies. Within the team, we're working with a tagged version that has almost 10,000. And this will be very similar to the final release, which is planned for July of next year. We should have stopped observing by now, but the pandemic shutdown kind of changed the schedule a little bit. So actually we're still observing at least through to August 25th, when New Mexico, the Apache Point Observatory will go into summer shutdown. And then exactly what happens when it opens up again is a little bit unclear. We're about to hand over to Sloan 5, but because of the COVID shutdown, they're not quite ready with some of the instrumentation. And so it's all a bit up in the air, but we're approaching 10,000 galaxies. Okay, and in case I drop into this acronyms, I just wanted to tell you a little bit about the data and how it's reduced. So we have a data reduction pipeline, which goes from the telescope through to turning it into a data cube on a half arc second spaxel grid. So the spatial resolution of the grid is a half arc second, although the actual resolution of the image is about 2.5 arc seconds. And then we also have a data analysis pipeline, and this is the thing that measures all the different properties. So it measures all the velocities, spectral index measurements, and all things like that per spaxel. Okay, so now how about H1-MaNGA? So why did we decide we wanted to do H1-MaNGA? Well, MaNGA is a great optical survey, but there's lots of information we can get outside of the optical range. And so the idea behind H1-MaNGA was to build on MaNGA's key questions, which are themed around the birth, growth, and death of galaxies. And every one of the MaNGA key questions, actually, you can talk about how H1 and understanding of cold gas content or dynamics of the galaxy is important to kind of complement them. MaNGA's strengths, obviously, in numbers. The 10,000 sample was justified by looking for correlations on lots of different axes. And so for the H1 follow-up, we wanted to get as close to that full sample as we could. And so the idea is to go big and get lots and lots of data for galaxies. Okay, so what about existing data? So here is a little summary of existing or future H1 overlaid on the footprint of MaNGA. This is a little bit complicated. So let me talk you through it. So the gray circles here is effectively the Sloan imaging footprint on which MaNGA was targeted. So any one of these gray circles is a potential MaNGA plate, one of those plates with 17 galaxies. And then what MaNGA did was basically optimize survey strategy or survey efficiency and do as many of these as possible. And so they're color coded in different colors, for purple being observed at the time this plot was made, which is I think more than a year ago now. And then tier 1 is like the next set of priority for observing, and tier 2 is we're probably not going to observe. And the gray is you could observe, but we're almost certainly not going to get to them. Okay. And so overlaid on this is lots of little boxes which show various different H1 related data or other data. So really important here is alfalfa, which is Arecibo. untargeted H1 survey. So it just scanned the sky. Any galaxy that has H1 in the redshift range alpha alpha was sensitive to the sensitivity limit will have a detection. What was interesting is MaNGA, the survey sort of efficiency favored the more northerly observations early. So most of the early MaNGA observations were north of where alpha alpha has data. There is a survey called Aperitif, which is a planned survey, or Aperitif is the instrument, but there's a planned H1 survey using this facility, but hasn't fully started yet. And then of course there's things like SKA coming along, but of course that's in the south. So the northernmost limit of that is well below where most of the MaNGA galaxies are. So we thought Green Bank was ideally suited basically to do a follow-up survey. And the strategy was to go to the same depths as the alpha alpha survey so we can combine it with alpha alpha. That also partially motivated the redshift limit, although it's also motivated by where you can kind of expect a reasonable detection fraction of H1. But other than the redshift cut, we observe every galaxy in MaNGA. So there's no cut on morphology or color or expectation of H1 content. So we get a full census of the H1 content of the MaNGA sample. The MaNGA sample is, has sort of fairly complex selection criteria. It's all explained in a paper by Wake et al. This was done to kind of make a representative sample, and because it's embedded in the Sloan main galaxy sample, you can reconstruct a volume limited sample from this. But in any case, it has these two stripes, a primary and a secondary sample, where there is a dependence on redshift and stellar mass by design. And what you end up with is this full histogram here is a fairly flat stellar mass distribution from 10 to the 9 to 10 to the 11 solar masses. By putting in this cut at 0.05, the H1 MaNGA sample loses preferentially the higher mass galaxies, which are ones which have lower H1 content typically anyway, so are harder to detect. So they're higher redshift and have lower H1 content, and so we made the choice to not go after those. Okay. So we've had a lot of Green Bank time, and we're very grateful for that. We started back in 2016 with 193 hours, which was awarded as filler time, and that ran in February 2016 to 2017. In 2017, we had a much larger program approved and ended up getting more than 1,000 hours from December 2017 through to February 2018. We had some time in the 2019 A semester, and then we took a bit of a break to make sure we caught up with our data reduction, and we're back on the telescope for this semester. So the 20B semester, we were awarded not quite 600 hours, and we've already had 22 and a half in August, almost every day in August so far we've been scheduled. So like every other Green Bank program, the observing is scheduled dynamically. In the first year, we did this remotely, so we had a small team of remote observers doing this observing. Since 2017, we got approval to be run in operator-led mode. So there's a Python script that runs within Astrid, and it picks based on the current location of Green Bank. At the time we take over the telescope, it selects the most sensible target for a minimal slew time, and it basically continues to do that and goes from target to target. This is monitored in real time by the operators, not us. So we're not remote observing in real time, although we do check in sometimes, particularly at the beginning. And then either myself or Dave Stark will check the data at the end of each session before the next one to kind of update we have catalogs that have codes in to say, you know, how much more time we need per galaxy. So we update all of that and check the data quality, check how much time we've lost because of RFI, for example. So that's how the observing runs. This is a slide really more for my optical colleagues, but just a reminder that in the MaNGA bundles and the typical galaxies that are in MaNGA are between 12 to 33 arc seconds in diameter, so about half an arc minute, whereas the Green Bank beam at 21 centimeters is around about 9 arc minutes. So obviously we're sensitive to H1 in the galaxy and in anything near to the galaxy in space. Or redshift though, right? So this again, from my optical colleagues, just reminding what you get with a H1 spectrum. This is a nice textbook version. You know, we center the observing on the optical redshift of the galaxy, the known optical redshift. Every galaxy we observe with Green Bank has already been observed with MaNGA. And so in an ideal world, we get a nice H1 signal that's at the same redshift. Spread is caused by rotation. We have the rotation of the MaNGA galaxy too, so we can tie it to that. And then of course the integral under the line here is the H1 mass, or is proportional, directly proportional to the H1 mass divided by the distance squared. So we get lovely data. And we're doing pretty well, getting lots of data. So again, lots of numbers here, but just for those who like to see all the details. The first year of data was published already. Last year we published it and was released as part of the SDSS data release 15 as one of these so-called value added catalogs. There's an infrastructure to do that. That was around about 300 galaxies, a bit more than 300, a bit less than 200 of which were detected for an average time per galaxy of 35 minutes, which has been holding quite steady. We have a much larger sample that's available for use and that will be published by Dave Stark. Stark et al. Is in prep, hopefully soon to be submitted. And we're targeting releasing that as part of the final Sloan 4 data release as a VAC. And then, you know, we have a little bit more than this, or well, I guess quite a lot more than this, that is observed but not fully reduced yet. And so we'll see how quickly we're able to get through the reduction, whether we can get that into the Sloan DR17 as well, or if it will be later. At this point, I wanted to make a quick shout out to the observing data team, and particularly Dave Stark. So Dave's a postdoc at Haverford right now. He moved to start work at Haverford about a year ago. He is responsible for the observing script and also a beautiful data reduction script, which makes the data reduction really accessible. And so we've had many, many undergraduates. So even before I was at Haverford, REU placements who worked with me in Portsmouth did this, but at Haverford, you know, lots of students who want to do research for credit, some who do work study paid research during the semester, and then big summer program. And so this was the summer group that we had working with Dave and me this summer. And many of these students, smiling here in our Zoom group meeting, have helped with some data reduction. Should also mention several colleagues from the MaNGA team have helped as well, particularly Zach Pace, who helped with remote observing that first semester. Okay, so some results. So this is the small sample from the 2016 observing. So just showing that our survey strategy works. This solid line here was our expected detection limit. And you can see the detections are almost all above it, occasionally below, and our non-detections are almost all below it, occasionally above, usually where we've been impacted by RFI. And so we've actually got less sensitive data than we intended to. But our rough limit is around about 10 to the 9.4 solar masses at 9,000 kilometers per second at the median redshift of the sample. Here are some example detections along with the MaNGA galaxy that they correspond to. So this was again data reduced by an undergraduate and the plot made by her. From that 2016 data, we were able to recover known scaling relations of H1 and stellar mass. So this is comparing the H1-MaNGA detections, weak detections and upper limits with the stellar mass to H1 mass relation from alfalfa data. And then also, you know, how we recover the sort of expected relationship between H1 and star formation, although with some interesting galaxies. So the majority of our detections are on the star forming sequence here, so the high star forming, whereas most of our non-detections are in the not star forming part of this plot. So this again is MaNGA data in the background, but with the H1 data overlaid. We have a much bigger sample than this now, and so Dave in particular and a number of the students actually we had working with us this summer have been working on projects that leverage this bigger sample. So here's an example from Dave's upcoming paper where he's looking at scaling relations of H1 gas fraction, so the green bank data on the y-axis, and in this example with the equivalent width of O2. This is the strongest correlation with a single equivalent width, so emission line in the MaNGA data. And Dave has used survival analysis here so that we're able to use all of the non-detections to the best of our ability. So stay tuned for more on that. And I just wanted to highlight this one nice science result by someone else. So this is not someone who's even part of MaNGA or the H1 observing, but use the public data that we that we had available. So Guido Roberts-Borsani used sodium D line from the MaNGA data. So here we have the MaNGA data to detect outflows. So the outflow is the blue line here, which is an absorption line that is blue shifted relative to the main part of the galaxy, revealing an outflow. And then Guido then stacked the H1 data for outflows or not outflows and found that there was a significant difference between the H1 content and the H1 line profile shape between the two samples, which is very interesting. Okay, I'm almost through, but someone always asks, what about molecular hydrogen? Neutral hydrogen is not the only cold gas in a galaxy. Hopefully I've already given you a sense that collecting all this neutral hydrogen data is already a big enough job. So doing molecular hydrogen as well would be a lot. But we are collaborating with various groups who are doing this. So for example, the Jingle survey, which is JCMT legacy survey led by Amélie Santonge, has got some significant overlap with MaNGA. I still need to run the numbers, latest numbers on that. I hadn't done that when I was preparing for this talk. But some tens of galaxies with JCMT data. AlmaQuest is also an initiative to basically collect together all ALMA observations of MaNGA galaxies done by different PIs. This currently has 44 MaNGA galaxies with ALMA data. And the exciting thing about the ALMA data is this is at comparable resolution to MaNGA. So it's roughly 2.5 arcsecond resolution. And so here's an example where you have the star formation rate in the bundle from the MaNGA data, and then the molecular hydrogen from ALMA. And you can combine the two together to get things like star formation efficiency and gas fractions, CO fractions here. We have also done a trial with Argus on GreenBank. So Jay encouraged us to put in for a small amount of time to do this, and Dave Stark took a lead on this and led with the observations as well. And we tried out some nodding observations and some mapping observations because of the higher frequency, lower wavelength, the resolution of observations with Argus is such that some MaNGA galaxies do need to be mapped, the bigger ones. We think this will work great for targeted follow-up, but there were quite large overheads, much larger than with L-band. And so, a very large program, it would be challenging with this. And so we haven't explored doing much more with this yet, but here's an example of a detection of CO in a MaNGA galaxy using Argus and the GreenBank telescope. So with that, just a quick thank you to GreenBank and particularly to the operators for running our program for us. Thanks very much.
All right, thank you, Karen. So again, if people have questions, please feel free to use the chat or the Q&A part. First question came through is asking Karen whether or not these are Vegas observations and also whether or not there are any other lines to the other IFs that are available.
These are Vegas observations. We haven't looked in detail if there are other lines available. We haven't planned that.
And I'll put a second plug in. Your Argus observations looked very intriguing. I would hope that somebody from your team is thinking about coming to the Argus 144 meeting where we could solve your time issue there with the observations.
Sure.
All right, do we have any other questions? Just have to give it a moment. All right, well, if not, thank you again, Karen, very much. Thank you, everybody else, for your time, for coming this afternoon. Jay will be announcing out our next talk, which will be in approximately 2 weeks' time. So thank you guys very much. And Karen, thank you very much for the fantastic talk. Appreciate it.
Thanks, Karen.